another academy. In this video, we are going to discuss about permutations. Let's start with the definition. Let A be a set containing n elements. Okay. Then a bijection from A onto itself is called a permutation. So, permutation is nothing but a mapping which is both one and onto. Okay. So, we take a finite set. We take that set as the domain and that set as the range. And we define the bijection from A onto itself. So there may be so many different bijections between the two sets, no? So the collection of all bijections, that is called what? Permutation, right? And the set of all permutations of A is a group under composition of functions. Okay, so that is, if you collect all permutations of the set, we define an operation, okay, right? And that operation is nothing but composition of functions. So under this operation, it forms a group. Okay, and what is the name of the group? Symmetric group. Symmetric group of degree n. What is this n? N is the number of elements in the given set A. And how many elements will be there in Sn, symmetric group? The symmetric group will contain n factorial elements. Okay, now let's see some examples. The first one is A equal to 1, 2. The set is containing 2 elements. So let's see what is S2. So S2 will contain 2 factorial elements. Already I told you, no, if there are n elements, then the symmetric group will contain n factorial elements. Here 2 elements are there. So S2 will contain 2 factorial equal to 2 elements. So how to write the elements? Just you put 2 brackets. Okay, in the first row you write 1, 2. The first row of the permutation usually contain elements of the set. So 1, 2, 1, 2. Next, in the second row you have to write the images. Okay. So first one, let it be the identity mapping. 1 goes to 1, 2 goes to 2. Then for the second one, you just interchange the elements. 1 goes to 2, 2 goes to 1. Okay, that's all. So this is the symmetric group on 2 symbols. Okay, so actually in lower classes you have studied mappings, no? So how do you define mapping? This is set A and this is set A. This is domain, this is codomain. You write the elements of domain this side, elements of codomain this side. Then we map 1 to 1 and 2 to 2. This is one function, one bijective function defined on the set A. Another bijective function is 1 goes to 2, 2 goes to 1. Simply these two things I have written here as permutations. Okay, so this is called what? Permutation group. This is the identity permutation. Next one, permutation on 3 symbols. A equal to 1, 2, 3. Then S3 will contain how many elements? 6 elements. 3 factorial equal to 6, no? So 6 elements it will contain. So what are the 6 elements? Just you blindly put 6 brackets. In all the brackets you put 1, 2, 3 as the first row. The elements of the set you have to write in the first row. Then for the second row, first let us write the identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3. Then for the next one, just you interchange the 2 numbers. Okay, 2, 3, no, here. So here you have to write 3, 2. Next, for the next element, you take 2 as the first entry. Here you have taken 1 as the first entry, no. So here 1, 2, 3, 1, 3, 2. Similarly here 2, 3, 1, 2, 1, 3. And for the next one, take 3 as the first element. 3, 1, 2, 3, 2, 1. That's all. So these are the 6 permutations and this is the identity permutation. Okay. So this itself forms a group under composition of functions. So now in the next example, let me tell you how to define, how do we find the composition of 2 permutations. Okay. Now let's see the problem. For alpha equal to 1, 2, 3, 4. 2, 4, 3, 1 and beta equal to 1, 2, 3, 4, 3, 4, 1, 2. Compute alpha, beta alpha, alpha inverse, beta inverse. So all these things we are going to find out for these 2 given permutations. See, these 2 are permutations taken from S4, permutation on N 4 symbols. Okay, right. Now how to find this alpha, beta and beta alpha? Before that, see, f is a function from x to y and g is a function from y to z. Then we can define g composite f, isn't it? Then g composite f is a function from x to z defined by g composite f is equal to g of f of x. So this composition of functions is being used here for permutation. See, first you have to find alpha, beta, no? Very simple. For writing the product also, first you write the first row as 1, 2, 3, 4. Then for their images, how to find the images under alpha, beta. See, You have to alpha beta means you have to strictly follow the order. Alpha comes first and then beta, no. So here see 1 goes to 2, 2 goes to 4. So 4 is the ending element, no, that 4 you have to put it here, right? See, I want to find the image of 1 under this alpha beta transformation. That means under alpha 1 goes to 2. Okay, carry on this 2 here to beta. Under beta 2 goes to 4, so 1 goes to 4, right? For finding the image of 2, for finding the image of 2 under alpha beta, look at alpha. 2 goes to 4, 4 goes to 2, so you have to write 2 here. Next for 3, 3 goes to 3, 3 goes to 1, so 1 here. 4 goes to 1, 1 goes to 3, so 3 here. Okay, right? That is, you have to continuously look at alpha and beta together. So this is the product alpha beta. Next one is beta alpha. Beta alpha means you have to start with beta and then you have to go to alpha. So as usual, you write 1 2 3 4 in the first row. For the second row, for the image of 1 under beta alpha, 1 goes to 3, 3 goes to 3, so 3 here. Next one, 2 goes to 4, 4 goes to 1, so 1 here. Next one, 3 goes to 1, 1 goes to 2, so 2 here. Next one, 4 goes to 2, 2 goes to 4, so 4 here. Okay, this is beta alpha. Okay, that is alpha beta is not equal to beta alpha. If you look at these two things, you can easily identify alpha beta is not equal to beta alpha. Already I told you Sn forms a group, but it is not abelian for n greater than or equal to 2. Only S1 and S2 are abelian groups. S3, S4, S5, all other things are non-abelian groups. Okay. So definitely alpha beta will not be equal to beta alpha. Next, let's find the inverse. Alpha inverse equal to. For finding the inverse also, first you write the first row 1 2 3 4 as it is. Now alpha inverse, no, see 1. Look at 1 in the second row. 1. What is the pre-image? 4. That pre-image you have to write here. 1 here is 1, no, a 1 is having pre-images 4. So here it has to be 4. Then for 2 is here, no, for 2 the pre-image is 1, so 1 here. For 3 the pre-image is 3, so 3. For 4 the pre-image is 2. Okay, so for finding alpha inverse, you have to look from the second row. And for finding beta inverse, simply you write 1 2 3 4 in the first row. Okay, here 1. For 1 pre-image is 3, so 3. For 2 the pre-image is 4, so 4 here. For 4 the pre-image is 2. Okay, and for 3 the pre-image is 1. So this is alpha inverse and this is beta inverse. Hope you understand how we have written all these things. The next one concept in permutation is cycle. Okay, that is, suppose if P is a permutation on n symbols. Okay, now P equal to A1, A2, A3. P means we usually write the permutation in two rows, no? First row containing the elements of the set and second row containing their images. But while representing them as a cycle, we just write it as a single row. A1, A2, A3, etc. AR. So the single row is called a cycle of length R. If, when will you say this is a cycle? Image of A1 equal to A2, P of A1 equal to A2, and image of A2 equal to A3, etc. Image of AR minus 1 equal to AR, and finally image of AR equal to A1. Okay, that is, see, while writing the permutation, you write the symbols on the first row and their images on the second row. But in cyclic representation, you write both of them in a single row. So here, how will you find the images? The image of the element is equal to the next element which is on the right side. Image of A1 is A2. Image of A2 is A3, etc. You have to proceed like this. And for the last element, image of AR, it is equal to what? A1. So this is called what? Cycle. And what is the length of the cycle? How many symbols are there? You count. That is called the length of the cycle. Right? And then two cycles are said to be disjoint. When will you say they are disjoint? They don't have any symbols in common. Okay. When the given two cycles are not having any symbol in common, they are said to be what? Disjoint cycles. And product of disjoint cycles is commutative. This is very important property. Okay, only the product of cycles is commutative only when they are disjoint. If they have any one symbol in common, it will not be commutative. Next one, product of cycles need not be cycle. Suppose if you take two cycles and you take product, that need not be a cycle. Next one, any permutation can be expressed as product of disjoint cycles. This is an important property which we are going to use for doing problems. Another one is decomposition of permutation into disjoint cycle is unique except for the order of factors. That is, if a permutation is given, you can write it in so many different ways. Okay, and it is unique up to the order of the factors. Okay, next one, order of a permutation is equal to, whenever we talk about group, we talk about order of the element. So here Sn, we said it is a group containing n factorial elements. So here also we have to find the order. No, order of a permutation is nothing but LCM of length of disjoint cycles. Okay, while doing the problems you can understand it better. Just you remember LCM of length of disjoint cycles. Now let's see the problems. Write the following permutations as a product of disjoint cycles. Also find its order. So some permutations are given. First I am going to write them as product of disjoint cycles, and then I am going to find the order. See, this is the first permutation. It's a permutation on 5 symbols. 1, 2, 3, 4, 5 is given now. So how to write the cycle? See, start from 1. 1, 4. Okay, then 4 is sending here. No, look for 4 here. 4, 1. 1, 4, 4, 1. So that is a single cycle. Next one, next element is 2 goes to 2, no need to write. If the element goes to itself, no need to write. Then next one is 3, 3 goes to 5, 5 goes to 3. So 3 comma 5, not comma 3 5 you have to write. So that's all. So all elements are comes under here. So this is the cyclic representation of this permutation. Okay, so here it is written as product of two disjoint cycles. Now how to find order of this permutation? Order of this permutation equal to LCM of length of disjoint cycle. What is the length of this cycle? Length of the cycle means number of symbols in it. How many symbols are there? 2. So 2, and what is the, how many numbers are there? 2 numbers. So 2 comma 2. What is LCM of 2 comma 2? 2. So this permutation is of order 2. That means if you square this permutation, you will get the identity permutation. What do you mean by order of an element? That is, if order of element is n, that means a power n equal to e, the identity, isn't it? So here order of this permutation is 2. That means if you square this permutation, you will get the identity permutation, right? Next permutation, 1, 2, 3, 4, 5, 3, 4, 5, 2, 1. How to write the cycles? 1, 3, 1 goes to 3, no? So 1, 3 you put. Next 3 goes to 5. So 5 you put. Next 5 goes to 1. So cycle ends. So if you get the first element as the image, there you have to finish the cycle. Next, remaining elements, 2 goes to 4. So 2 goes to 4 and 4 goes to 2. That's all. Okay, so when you get the starting element as the image, you have to finish the cycle and you have to start again. Okay, so 1 goes to 3, 3 goes to 5, 5 goes to 1. So that you have to write it like this. So 1 goes to 3, 3 goes to 5 and 5 goes to 1, right? And 2 goes to 4, 4 goes to 2. So 2 goes to 4 and 4 goes to 2. Right? So this is written as product of two disjoint cycles, and their order is equal to LCM of length of this cycle is 3 and length of this cycle is 2. What is LCM of 3 comma 2? 6. So this is of order 6. That means when you take the power of this permutation to 6th power, then at that time only you will be getting the identity permutation. Next one. Here the permutation itself is given as product of cycles, but the cycles are not disjoint. You see 1, 2, 3, 4, 3, 4, 5. 3, 4 are appearing on both the cycles, no? So this is not disjoint cycle. Okay, but what is the question? We have to write the permutation as product of disjoint cycles. So first you have to, from this given, you have to write the permutation and then we will write it as disjoint cycles. 1, 2, 3, 4, 5, you write it here. Now, how to write the permutation? See, 1 goes to 2, but 2 is not here, no? Just so simply write 2. Next one, 2 goes to 3, but 3 goes to 4. Product, no? So, how will you write? 2 goes to 3, 3 goes to 4. So, here 4 here. Next one, 3. 3 goes to 4, 4 goes to 5. So, 5 you have to put. Okay, how did you do product of permutation? In the same way only I am doing here for cycles. Next one, 4 goes to 1. 4 is the last element, no? So what is its image? 1. 4 goes to 1, but 1 is not here. So simply put 1. Next one, 5. 5 is not here. Only here it appears. So 5 goes to 3. That's all. Okay, so this is the permutation for this cycle decomposition. Now let us write product of disjoint cycles. How will you write? 1, 2, 1, 2, 2 goes to 4, 4 goes to 1. So starting element na, so close the cycle. Next one, 3 goes to 5, 5 goes to 3. Okay, so this is the product of disjoint cycle. You see the difference. So the same permutation, but we have written in two different ways. This is not disjoint cycle. This only represents disjoint cycle. So order we can calculate only with this cycle. Order equal to LCM of 3, 2 equal to 6. Next one, this is also again of the same type. The permutation is given in terms of product of 3 cycles, but they are not disjoint. They have, these two have 3 as common and these two have 4 as common. So first let me write the permutation and then I will write the cycle decomposition for this. Now 1, 2, 3, 4, 5 you write in the first row. Now 1 goes to 3, 3 goes to 4, 4 goes to 5. So 5 here. Next 2 is not here, no, that means 2 is fixed. So 2 goes to 2 only. Next for 3, 3 goes to 1, right? After that 1 is not appearing anywhere here. So simply write 1 here. Next one 4, 4 goes to 3. After that 3 is not appearing here. So 4 goes to 3. Next one 5, 5 goes to 4. After that 5 is not appearing here. So 5 goes to 4. See, whenever you are computing the product, you have to proceed only in the right hand side only. You should not go on the left hand side. See, for finding the image of 5 is not appearing here. Only in this one 5 is appearing. Now here 5 goes to 4. After that you have to look for 4 in the next right side cycles, but there are no other cycles on the right side, no. So 5 goes to 4 only, simply you have to write. You should not go back here. 5 goes to 4, 4 goes to 3. That you should not do. Okay, only in the right hand side you have to move. If there are no symbols on the right hand side, just you write the image. So this is the permutation. So what is the cycle representation? 1 goes to 5, 1 comma 5, then 5 goes to 4. So 4 and 4 goes to 3 and 3 goes to 1. So when 3 goes to 1, that's all. 2 is fixed, no, so no need to write. And what is the order? Only one cycle is there and it is of order 4. So fourth order permutation. Next one, 1, 2, 3, 1, 6, 5, 4, 3. Again, not disjoint. See, write 1, 2, 3, 4, 5, 6. 1 goes to 2, no 2 here. So simply write 2. Next 2 goes to 3, 3 goes to 1. So 1 here. Next one, 3 goes to 1, 1 goes to 6. So 6 here. Next 4 goes to 3. That's all. No other permutation here. So 4 goes to 3. Next 5. 5 goes to 4. Next 6 goes to 5. Okay. So this is the permutation and cycle decomposition. 1, 2. That's all. Next one 3, 6, 5, 4. Okay. And 4 goes to 3. So that's all. So and here the order equal to LCM of 2, 4 equal to 4. Next this one 4, 2, 1, 5, 3, 4, 2, 6, 5, 6, 7, 1. Not disjoint cycles. So let me write the permutation. So here it is on 7 symbols. 1 goes to 5. No 5 here. So 5 goes to 6. 6. Next one 2 goes to 1. 1 goes to 5. 5. Okay, if the symbol is not in the middle cycle, leave it. You go to the next cycle. Next one 3 goes to 4. That's all. 4. Next 4. 4 goes to 2. 2 goes to 6. 6 goes to 7. So 7 here. Next 5 goes to 4. 4 goes to 2. So 2. Next one 6. 6 goes to 2. Sorry, 6 goes to 3. And 3 is not there, no. So 3. Next one 7. 7 goes to 1. So this is the permutation and the cycle representation is 1, 6, 3, 4, 7, 1, no. So close it here. Next remaining elements 2 goes to 5, 5 goes to 2. So 2, 5. And order is equal to LCM of 5, 2 equal to 10. Okay, so this is how you have to find the cycle decomposition and the order of the given permutation. So we have seen what is a permutation and how to write the permutation as product of disjoint cycles. There is one more decomposition of permutation, that is called transposition. Transposition is nothing but a cycle of length 2. Okay. Likewise, we can write any permutation as a product of transposition. Okay, if a permutation is product of transposition, R transposition and S transposition, then both R and S must be odd or even. That is, I am writing in one way, you are writing in another way. Okay, both may be same, but what should be there? That is, if I am writing it as R number of transposition, you are writing it in terms of S number of transposition. Both R and S should be what? Both are odd or both are even. The numbers may be different, but they should be both odd or both even. Next one. A permutation is called an even permutation or odd permutation according as it is expressed as product of even number of transposition or odd number of transposition. In numbers we say no odd number, even number. In that way, in permutation, a permutation is even means it is expressed as even number of transposition. Permutation is odd means it is represented as odd number of permutation. Okay. Now let's see this permutation. 1, 2, 3, 4, 5, 6. Permutation on 6 symbols. So for writing it as product of transposition, first you decompose it to disjoint cycles. So what is the cycle representation? 1, 2, 3 and 4, 5, 6. Okay. After that, let us write the transposition. 1, 2, 3 is there, no? That you have to write 1, 2, 1, 3. Okay. First number is fixed with second number and first number with third number. 1, 2, 1, 3. So this is the transposition for the first cycle. For the second cycle in the same way. 4, 5, 4, 6. So how many transpositions are there? 1, 2, 3, 4. So this is an even permutation. Next 1, 2, 3, 4, 5, 6, 7, 8. Right? First, like, let us write the cycle. 1, 3, 2, 4, 1. That's all. Next one 5, 6. That's all. Next one 7, 8. Already these two are transpositions only. So you keep them as it is. Only this cycle we are going to decompose into transposition. How will you write? 1, 3, 1, 2, 1, 4. So 3 transpositions. Okay. And 5, 6, 7, 8. So how many totally are there? 5. So therefore the given permutation is an odd permutation. Next one, here they have written it, they have given it as a product of cycles 1, 2, 3, 4, 3, 5, 6, 6, 7. The cycle is not disjoint. So first let us write the permutation and then disjoint cycle. After that we will write the transposition. Then only you will get the correct result. Okay, right. So what is the permutation? 1, 2, 3, 4, 5, 6. 1 goes to 2. That's all. So 2. Next 2 goes to 3. 3 goes to 5. So 5 here. Next 3 goes to 4. After that no 4. So 4. Next 4 goes to 1. No 1 here. So 1. Next 5 goes to 6. 6 goes to 7. So 7 here. Next 6 goes to 3. That's all. So 3. Next 7 goes to 6. That's all. So what is the cycle representation? 1, 2, 5. Right? 1, 2, 5, 7, 6, 3, 4. That's all. So it is represented as a single cycle. So what is the transposition? 1, 2, 1, 5, 1, 7, 1, 6, 1, 3, 1, 4. So this is an even permutation because how many transpositions are there? 6 transpositions are there, no? So it's an even permutation. Next, let's see some of the properties. The product of two even permutations is an even permutation. The product of two odd permutations is an even permutation. Product of an even and an odd permutation is an odd permutation. See, for finding the product of permutations, you have to follow the addition of natural numbers. See, when you add an even number with even number, you will get an even number, no? When you add an odd number with an even number, what will you get? Odd number with an even number, you will get an odd number only. And if you add two odd numbers, it will be an even number, no? The same pattern will be followed here for permutation. So 2 even means it's even. 2 odd means that is also even. 1 even, 1 odd means that is odd. Then inverse of odd is odd and inverse of even is even. Identity is always an even permutation. Next one, alternating group. Alternating group means Sn we have seen no symmetry group. That is permutation group on n symbols. In that, from that permutation group, you collect only the even permutations. That will form a subgroup and that group is called alternating group and it will contain exactly n factorial by 2 permutations. In Sn, n factorial elements are there, no? In An, it will be half of the elements. Then every cycle is a permutation, but every permutation need not be cycle. We have seen no permutation can be written as product of disjoint cycles only. It always need not be a single cycle. Okay. For n greater than or equal to 3, Sn is non-abelian and in that case, identity element is the only element which commutes with all other elements of Sn. Okay. That's all. Thank you.